Okay, so here's the remaining timetable, and so as you know, we try to run 11 lectures and 10 tutorials normally when it's appropriate. And today we are already here. It's already June. Can you believe that? Half the year is nearly gone. Where's all the time gone? Soon it'll be Christmas. It won't be that far. By that time, you will all be finance professionals. Anyway, so we have one more tutorial now. As you know, the exam is next Saturday, so it makes absolutely no sense to have a tutorial in the morning so that you have an exam in the afternoon. I'm going to leave you alone next Saturday. So today will be the last time that you have to rise so early in the morning on a Saturday to come here to listen to mathematical modeling, okay, and stochastic calculus. I have actually planned for another final tutorial, which will be on Tuesday, and it will be in the evening. So I hope for our part-time friends, if they wish to come, you can, but don't feel you have to. I will make that available also. I probably will not take attendance either because I know some people may have difficulties. So just to be fair, we're not going to count that. But it will be opposite, just the other, yeah, it really is just across the road. I booked a room. So I'm going to try and tidy up the loose ends and maybe just, try to guide your expectation on the final exam and so on. Regarding the exam, it will be in 1 week's time. Did you guys did we agree it would be 3 hours? Keith kind of asked for a vote, right? Do you want 2 hours or 3 hours? I think that's kind of a silly question, because if it's 3 hours, you can always walk out after 3 minutes. I know you can't walk out after 3 minutes. You have to stay at least 30 minutes. But anyway, it will be downstairs. It's AIT. Okay. I don't know if our normal classroom is actually available. I couldn't find any records, so I thought, okay, I'm just going to book a room that I know will be available. So it will be downstairs. You know, AIT T04, right? Just downstairs here. So the last tutorial is across the road. Okay, don't confuse the two. That's on Tuesday if you want to come. I will send all you guys invitations on that. And then the final lecture, of course, is across the road today. But the final tutorial, the final lecture and the final tutorial are across the road. So WMY 407 or whatever, that's the lecture. The tutorial is YIA 401, but the exam is here. Okay? So like I said, you will receive invitations and they will be posted on Blackboard anyway. So the exam is a collection of short questions dealing with the 4 different parts, and then there's some calculations, but I don't think you need a very powerful calculate. No, you don't need that. Okay? You just need something that is functional. All right, now let me So I have here, like I said, some notes on skews and kurtosis and mean and variance, which some of you might have seen before. Maybe you haven't if you are coming from a different program. This is just different ways to characterize a distribution of any random process in order to determine whether it is a normal distribution or not. Now, you know about mean and variance. Mean is just the expectation. Variance is the second order deviation or standard deviation. Skew is actually the third moment, and kurtosis is the fourth moment. So it's quite neat the way it develops. The thing about mean and variance is that if I give you a whole bunch of numbers and I don't show you, the graph, and then you just go away and you use VBA or Excel, you calculate the mean and variance, there is absolutely no way you can tell whether that distribution is in fact normal or not. And here is an example of two distributions which in fact will have the same mean and variance. So immediately you can see that, well, if you just take mean and variance, it could be quite dangerous if that is all you use for your analysis. So that is why we introduced the idea of skewness. Skewness, for me, is just another word for symmetry. Is your distribution even symmetric, like a mirror, or is it not? If it is not even symmetric, it can't be normal, surely. Okay, and there's a definition on the right-hand side. So you can see here. I don't know if the red one is normal. I know the yellow one definitely is not. And the skewness will show for that. But that is not enough. Even if something is perfectly symmetric, so you don't have any skews, that by itself doesn't make a distribution normal, because you can have some really extreme cases, like the one that looks like the Eiffel Tower. Now this one is perfectly symmetric, and if you calculate the mean and the variance, they would look pretty normal or pretty unremarkable. And if you calculate the skews, also there will not be any skews, but there's serious kurtosis, which is to say the peaks and the tails do not conform to the requirements of a normal distribution. Now, I want to just quickly introduce this, because we're going to come back to that in just a moment. Okay. Anyway, this is not hard. What I do want to do now is to just give you a reminder of what we did last week. It's not this one. Here. Yeah, so last week we had a look at convexity adjustments. So I will just quickly recap on that. Now, so as I was saying to you, and this is a very useful and interesting topic of practical interest. The fact that when you are trading some interest rate products, and the euro dollar futures is a good example of that. One side seems to have all the advantages, no matter whether the market is going up or down, and the side that has all the advantages actually is the short side. Short futures. Short futures mean you are long rates. Short futures mean you are looking for the futures price, 98 or whatever, okay, which translates to a 2% rate. Short futures means you are looking for the price to drop, or you're looking for the rate to rise. It's a lot easier to say long rates. I'm long rates, I'm short rates. People know what you mean. Now, and the reason that happens is that if you are short futures and you are long rates, so your long rates, you want rates to go up. So when rates go up, you will make profit. But not only that, you earn interest on your profit, so you get profit on profit. Whereas down here, your long rates, but rates go down, your short futures and futures go up. Your long rates and rates go down, so you have a loss. So you have to borrow some money to cover your margin calls, but you need to borrow less, or there will be less interest costs. So there's less loss on loss. So if you have two parties, A and B, and A is short rates, sorry, I mean long rates, good morning, or short futures. Okay, I'm going to stick to the prices. Short futures. So B is long futures. So B is kind of permanently disadvantaged. And if you wish to draw a diagram, I guess it would look something like this. So A, okay, I'll bring you back to, so A is the party that is short futures and long rates. And B is long futures, therefore short rates. Sorry, long rates. You see, people really do get confused. And B is long futures, short rates. Then, now I'm going to do this in price terms. So, so this is the futures price, euro dollar futures price, and this is the P&L. So maybe right now the market is here. So this is 0. So right now no one makes anything. But A is short futures. So the moment the futures price start to go down, A will make a profit. But not only that, you make more profit on profit and less loss on loss. Now this is A's payoff. Now for B is the unlucky party on the other side. B is going to be, because B has to be like this, because B is on the other side of the trade. So your gains are my loss. So you can think of it like this. And convexity adjustment is all about one party having a permanent asymmetric advantage over the other. So B will yell out and say, hey, look, this is so unfair. So I want to be compensated. Is everyone okay with that? Hmm? Oh yeah. Yeah. I know. Right? Yeah, yeah. It should be. It should be like this. That's what you mean, right? Yeah, that's true. But you get the point, right? The departure from the linear outcome. Okay. Sorry, you're right. This is B. Okay. But you can still compare it. So if you compare it to this tangent, yeah, that's what you should be doing. Okay. Now, so last time we went through. Okay, so we now understand what is a convexity adjustment, and we know why it's there. And last time I even went through with you how to determine, or one way of determining that is if you use a very simple forward rate model, then you can simply, so this is a small change of the forward rate. The forward rate from time, looking at it at time t, so this is time t, the forward rate, so this can be 1 month later, and then a 3-month forward rate. It can be whatever you want, okay? So in the extreme cases, we look at a tiny, tiny, tiny portion. But anyway, so this is the forward rate, and this kind of goes back to what we were saying about interest rate modeling, which is it is very hard to model interest rate, I think, by giving it some kind of a priori formulation, the way that like Cox, Ingersoll, Ross, or Vasicek, the way they were doing. So the new class of models, at least, will simply take the existing forward rates that you can derive from the market yield curve, and then it tries to model on all these forward rates one by one how they might change. Now, the simplest model that people came up with after they suggested this approach was the Ho-Lee model. So I told you about that one. And then somebody else came along, Heath Gerald Morton, and suggested a more generalized approach, because the Ho-Lee version is actually just this one here. Is a very, very simplistic representation of what the forward rate is. Now, and then Heath Gerald Morton came along and said, hey, look, you can have a whole lot more variety, but the if you were to use this, then the process that is followed by, or a small increment of the forward rate will be given by this equation here. And I want to clarify that last time when I did the derivation for you, I was using this formula, which came from the Ho-Lee model. So it is based on the assumption that this simple model is valid. And then we went away, and then we actually derived why it is that, given that simple model, then the convexity adjustment ought to be a half sigma squared T1, T2. Now, let me just, is everyone okay with that? Yeah? Let me just share with you something. So, given that is one possibility for the convexity adjustment, let me just show you quickly a simple video on that. Okay, where this guy explains it quite well. It's only around 5 minutes.
Although this is another bilateral screencast on the convexity adjustment in its application to a $0 futures contract. Yesterday I talked about the key difference between a futures contract and a forward contract. The key difference is that futures contract, as it trades on an exchange, has a margin account and experiences daily settlement. The forward contract does not. This daily settlement creates a price difference, and in the case of the euro-dollar futures contract, a difference in the rates that increasingly matters over longer maturities and may not matter at short maturities. So the holder of the euro-dollar futures contract, that contract is marked to market on a daily basis. And that means as the value of that contract goes up, there may be excess cash in the margin account. As the value of that contract goes down, there may be margin calls. This creates daily cash volatility for the holder of the futures contract that the holder of the forward rate contract does not experience. This daily volatility is slightly more risk and implies that the futures rate ought to be higher. And so we can use an approximation, and there are several. This is the Ho and Lee approximation following John Hall from FRN Canada customers, where we're approximating the difference by saying that the forward rate is equal to the euro-dollar futures rate minus this convexity adjustment. 1/2 the variance of the change in the short-term interest rate multiplied by T1 multiplied by T2, or the product of T1 and T2. T1 is the time to delivery of the euro-dollar futures contract, and then T2 is always going to be 90 days later, because the euro-dollar futures contract refers to a 90-day LIBOR interest rate. So now I'll use John Hall's actual.
I'll pause for a moment now. Notice that he never explained why it's a half sigma squared T1 T2. Now, you know me. When I see that, I don't like it. I want to know why. Where did that come from? So that's why last time we derived that based on the Ho-Lee model. And in fact, if just pause for a second, there is a technical note that John Howell wrote regarding convexity adjustments for euro-dollar futures. Now, this one is available in the public domain, or it was, but it's kind of hard to find sometimes. So I've actually downloaded it and uploaded to Blackboard. Don't worry about this unless you are very intellectually curious, and I know all of you are, and if you have some spare time, but this is not going to be part of the exam. But even here, it's not really explained so well. So that derivation that I shared with you last time, I did it at home in longhand. So that's the background for that. Okay, so let's continue.
Example, just to show you the application of this. And so first the assumption is that we have an 8-year euro-dollar futures quote of 94.
Now this is a bit of an extreme. He is looking at the forward rate. I mean, I guess you can you can do it if you want to, but you wonder what would be the purpose of that. So he's looking at a forward rate today. E equals to 0. 8 years from now. So what's 8 years from now? It will be June the 1st, 2027, and the 3-month rate between June the 1st, 2027 and September the 1st, 2027. Actually, these contracts don't mature on June the 1st. It's like the third week of June, but never mind. So it's an 8-year forward rate. A 3-month. Why would you worry about a 3-month interest rate 8 years from now? Beyond me, but this is just an academic example. Okay.
That means that the implied LIBOR rate on that futures contract is 1.94 or 6%. So the 6% is an annualized rate. However, it's compounded with the frequency of quarterly compounding, or the compound frequency is quarterly. So the first thing that John Paul does is convert that quarterly frequency into continuous compounding. So if you're an FRN candidate, I hope you know how to do this. We take the natural log of 1 plus that quarterly rate. Since it's a quarterly rate, I'm going to divide by 4, and then I'm going to multiply by 365 over 90. And I'm going to get 6.04, so that's still the implied annualized LIBOR rate for a quote of 94, but it's now on a continuously compounded frequency. So that's the futures rate right here in blue. Now I'm going to subtract the convexity adjustment. I need another assumption. I'll assume the volatility of the change in the short rate is 1.2%. And then delivery is in 8 years, so that's T1. And then T2 is going to be 8 plus 3 months, or 90 days. So that's 8.25. And so now I can apply the formula by taking the futures rate and subtracting 1/2 multiplied by the volatility, but I need the variance, so I'm going to square it, multiplied by 8 years to delivery, multiplied by 8 plus 3 more months. And inputting that formula, I've now used the futures rate of 6.04% and subtracted the small convexity adjustment, and that gives me an implied forward rate of 5.563. And as we said, we expect the forward rate to be smaller by the difference of this convexity adjustment, because the forward rate does not have the daily settlement and therefore does not have that increased volatility due to the daily settlement. This is David Harper, the Atlantic Journal. Thanks for your time.
You're welcome. One point which is worth mentioning is that what he's done here is he's taken a price or a rate from the futures market in order to try to work out the forward rate. I would say that the futures market is far more active and far more liquid, far more open, far more transparent. So this is likely what would happen in reality, which is the futures market is trading round the clock, Monday to Friday. And if a client comes to you privately, BlackRock, Fidelity, whoever, Alibaba, and wants to trade with you on a private, over-the-counter basis, then yes, you can look at the futures market, which is always there as a benchmark for you. Now, take a mental picture of these numbers, especially the two that I wrote on the board, which is the futures rate, which is higher, okay, because the long party, like I said to you, the party who is long futures is always disadvantaged. So if you are long futures, you want to buy at a cheaper price. And so I've written down, so because this is higher, this number, the futures number, the rate is higher, so the price will be lower. So if I'm buying that, that would be a compensation for me. Now, I think I know why he uses an 8-year number. So normally, you wouldn't trade that in isolation, just a 3-month forward rate trading out of 8, unless something is happen, but that's beside the point. I think the reason he uses the 8-year, and you can get futures contracts for short rates going all the way out, although the market becomes very thin. But the reason I think that he wants to do that is to show you the difference. Yeah, the difference is huge. The difference is practically 44 basis points. massive. So you can see that it's not a trivial thing at all. Now, I've actually, so I replicated this calculation at home using just a simple Excel spreadsheet. And it is kind of more, I did this myself, but it's more or less the same. And in fact, you can see that I'm getting the numbers that he's getting. So it's not 6.04, it's 6.038. See that? He rounded it up. So when I plugged in all the parameters that he's got here, so euro dollar futures at 94, and then the short rate volatility at 1.2%, delivery in 8 years' time. I think this is, yeah, so some of them I don't need any inputs, okay? Oh, this should be 94. This is hard-coded. Okay, I think I'm just using this cell here for the rate. The rest are calculated. So the numbers that you see are consistent with the numbers that are being shown. So the difference is close to 47 basis points. Now, that is because the time horizon is so extreme, but if you do something which is a little bit more reasonable, let's say 1 year from now, so what you're now doing is at t equals to 0, you are looking at the 1 year forward rate. So the 3-month rate starting in 1 year's time for 3 months. So this is 1 year and 3 months. I think you are going to get some numbers that do not look so extreme. Now, this is the convexity adjustment. That 47 basis points, I'm just taking the difference between here and here. That's all, okay? But if it was 1 year, there is still a difference, but it's a lot smaller. Can you see that? It's small, but you know what? The euro dollar futures market is huge. So everything will add up. And if short rate volatility was higher, now I'm getting half a basis point. No, 5 basis points, right? If you want to play around with this when you get home, feel free to do so. But I should make a small adjustment. So here is rates driven. So these two cells don't talk to each other. I guess they need to. So how would I do that? So if it's 94, then it is equal to 100 minus this divided by 100. Yeah. So the only inputs that you would need are this one, time to expiry. That's it. Okay. So just a little worked example so you get some idea of how that works. All right. Okay, I have actually uploaded a version, but I think this one's better. So I will reload it to Blackboard. Now there is I think there's so I said to you earlier that today I'd like to talk about moment generating functions and Gersdorff's theorem. So I'm going to try and start on that. Now, moment generating functions, as you know, and I already made some notes so that I don't waste your time just scribbling, is a very convenient and powerful way for you to get a feel for what the distribution or the characteristics of a random process might be like by setting up or incorporating that random process in a moment generating function of MGF, and then you take the derivative with respect to a parameter called lambda, and the first derivative is your mean, the second one is the variance, the third derivative is the skewness, and the fourth one is kurtosis. Now, you actually know that, so I just want to mention this here as an introduction. That is why I went through the means and variance and skewness and kurtosis. But this is not actually what I want to cover today. Okay, so that was just by way of introduction. And if you had a standard Wiener process, some asset with an expected return in the real world of mu, this is not u, this is mu, and then a volatility of sigma, then you actually can derive the expectation of that by using the moment generating function. Now, the technique that we are doing here is first you just set up the MGF, which is the expectation of this term, and YT, like I said, is this standard stochastic process, the Wiener process, and then this is simply the integral of the function inside. Don't worry if you can't follow, because this is all, I will give you all these notes and then I will give you the video as well, okay? And then, in fact, when you integrate it and you take out this term here, and I'm just if you rewrite all the terms, then you get this equation here. And then the trick here is if you multiply both the left-hand side and the right-hand side by 1, now I put 1 in quotes. What does 1 mean? 1 on the left-hand side is 1, but 1 on the right-hand side is actually this rather nasty looking term here. There's a minus sign, there's a plus sign, I haven't written that, but this is actually, the product of this is 1, so 1 equals 1. But what you then get, if you multiply this by 1, and if you multiply this by this term here, is you get this expression. And then if you rearrange that, the second part, so you take out all the terms that are common, or some of the terms for the exponential, you're left with this. Now, this is actually the area under just a standard normal distribution probability function. That is the formula. So that is actually 1. So you end up with just this, and which is equal to this when lambda is equal to 1. Now, like I said, so your mean is when you derive, or so when you take the derivative of m with respect to lambda, so the first order difference, so that is mu t, so that is the drift, and then when you differentiate it again, you differentiate this, okay? You get sigma squared T. So I am here just trying to show you how that comes about. So first, if you understand the MGF, which I think is covered in another course anyway, and then you plug in the standard Brownian motion, and it becomes this one here. You rearrange that this is e to the power of all of these. Okay? Sorry if that was not clear. Wipe out all these arrows. Okay, so that is a moment generating function. Now we'll come back to that in a moment, but I wanted to just recap on this because it will become useful in a moment. Remember that in Keith's lectures, I think it was 3, so he also made a mention of how you would do that change of measure. So 2 important theorems. The first one is Gersnoff. Now on this page, he says, pricing theory in a nutshell. I saw this and I asked myself, okay, how can I try to deepen the student's understanding? Do you remember that Superman thing I was explaining to you? How did that work? So Superman was just a normal guy, going about, doing the normal stuff. He goes into the telephone box, changes into the Superman uniform, does whatever he used to do. Now that he's done, he comes back out and becomes a normal guy again. So this is kind of what, so there are 3 steps. And this is what those 3 steps are. When you have a stochastic process and it has a drift of some kind, it is very hard to model that if it is not a true pure martingale. There are 2 ways to turn it into a martingale. One is to try to detrend it. I think the technique is called a Duke-Meyer decomposition or something. So you try to detrend it, and you might recall I even showed you a slide. I've forgotten which lecture, which tutorial it was. I showed you a slide. It might be a bit hard to find it now. Let's see if I can. Maybe it was earlier. I'll show you that here. Maybe it was even earlier than this. I think here. Yeah, this one. Okay. So you can try to detrend. You detrend the trend. You detrend the drift term. But the Gersnoff theorem was a recognition that the expectation has 2 parts. There's a probability part, and there's a payoff part. So why not we try to manipulate the probability instead of the payoff. And we actually discussed that earlier, but today I would like to share with you just an example of how it works, because if we don't do that, it's all just abstract. Someone asks you, what is the Gershon theorem? Oh, it's a change of measure. What is that? Or when we try to change the probability distribution in order to arrive at a pure martingale. Fine. And then they said, please show me an example. Right. Here's an example. Now, so let's say you have a stock. This looks like a stock price. You have a stock of some kind. And so it's fairly simple. This is a stochastic process. Now, this is what we see out there. So there's a real drift. This is not sigma t, mu t. Note that mu is not the risk-free rate. Mu is whatever is ultimately unobservable, but it is the required return for that asset. And if you write the price of yt is equal to ys, so s is less than t, to be an initial price plus whatever are the aggregation of the price changes. So you can define this. So the change of the price of yt over a small time to be the integral. Now, this itself would follow a stochastic process in that short period of time, t minus s, okay? The problem is, because of the risk premium, if you want to know the expectation of the price in time st discounted by the risk-free rate, it has to be bigger than the price of su discounted by the risk-free rate for this time. Now, let me explain what I mean by that. So I'm discounting by the risk-free rate. So let's say the risk-free rate was 1%, but this stock has a required return of 3%. Let's just say, I'm going to really rough approximation. So after year one, ST, this will be the expectation. And to year two, I know you need to compound it, but never mind, okay? I just want to be quick and dirty. Now, if you discount that by the risk-free rate, so 103 discounted back to today is 102. But 106 discounted back to today for 2 years is 104. So clearly you don't have a martingale here because this is bigger than. So in other words, when you discount future prices back to today, you don't get the same value when you discount by the risk-free rate. And that is what I'm trying to say here, this sentence here. So if you define EZT to be that variable when you are discounting future prices at any time by the risk-free rate up to that time, we can see that this is not a martingale. In fact, it is a sub-martingale. It keeps going up. And it's going up. Oh, sorry. You can see this is a very simple example. It is creeping up. So we can't model this the way we would like to. So the key question now is, and just look at what I typed, can you actually find an alternative probability measure, P tilde, such that you actually do have a martingale? In other words, you can replace this inequality by an equal sign. Now, can we do that? If you can, then you are getting somewhere, okay? Now, let's say we set up a new probability measure and we call it this. So this is n, I don't know what this Greek letter is called. This is not EZ, okay? Does anyone know how to pronounce this? Okay, let's call it EZ. Okay, so this is a new measure. We don't know what it is yet, but I'm going to show you. And the objective now is that under this new measure, whatever EZT is, capital EZ, okay, it will be equal to EZU. So at any point in time, so if this is the time now, this is the time U, this is the time T. Whenever I discount future prices back to today, they will be the same by the risk-free rate. So in a risk-neutral environment. Now this is when I need to make a reference back to the moment generating function. That's why I started by talking about that. The expectation on ST is actually equal to this. And now that actually just came from earlier. So I will just leave that as it is. So for now, what I've done is I've derived or I've set up a new probability measure called, I'll tell you what, I'm going to replace it with something I can pronounce. Let's just say rho. Okay, that's easy. So I'm going to put rho there. So when you use the moment generating function on the new probability measure, you are going to get this expression here. And we're just plugging in all the terms, including our new friend here. And if you take out the SU term, you are actually left with the exponential and a whole load of what I call the power term. Now, what is the power term? The power term is actually this one. That is, if you rearrange, if you just take this out, you take this out, you take this out, you can see that you get this one here. Now, here's the $1 million answer, okay? If you set, so what do we do now? Okay, if you set rho to be r minus a half sigma squared. So what I'm doing is I'm saying that, okay, I'm going to try and figure out what this should be, and I'm going to try this. Now, why do I want to try this? Well, you can see in a moment. Because if I do that, then the power term of the exponential becomes minus r t minus u plus, now I'm just going to plug in the rho as above, multiply by t minus u plus a half sigma squared t minus u. Now notice that the only thing that has changed is I have substituted what I think rho should be. And if you do that, it gets a bit messy. But I believe all the terms do cancel out with each other. Ladies and gentlemen, this is the beauty of mathematical elegance, I think. What does that mean? What the hell does that mean? It means by simply setting rho to be r minus a half sigma square, I have effectively made the power term 0, and e to the 0 is 1. So that means, so therefore, the expectation under the alternate measure of e to the r between a small time period from u to t, given as u, where u is less than t, will now be equal to su, because your power term is 0, so this term here will become 1. So therefore, we can take that to the other side. So e to the minus rt is equal to e to the minus ru su. Or if you want to simplify one step further, you can just say that zt, that is when you are discounting the future price by the risk-free rate in a risk-neutral environment, is equal to zu. So both of these will qualify as pure martingales. So that, ladies and gentlemen, is how you would tell somebody if they ask you, okay, please show me an example of how the Gersonov transformation really works in practice. How do you change the probability measure? This is how you do it. Okay? You just take a fairly standard random process for a stock that everybody knows, which is this. And then by using the moment generating functions, you can figure out what the expectation looks like for future prices. And then you speculate that, well, I need to do something to the probability distribution in order to make it a martingale, because right now it is not a martingale. So you do that, and then you apply the MGF. So you're left with this and a power term. You want to make the power term disappear. How? You keep trying until you find the right combination, and it turns out this is the right combination. You put that in, so this whole thing equals to 0. So you're now left with a martingale under the alternate p tilde measure. Okay? I wanted to share that with you because otherwise, I just felt that I haven't told you everything. Okay? So this is kind of augmenting this, and then my Superman story. Okay, the Superman story doesn't end there. You still have to tell people, how do you do it? This is how you do it. Okay. I will digitize all of these notes, and then I will share them with you. And in fact, if you go to Blackboard, I think the notes are available up to last week. So I will do it either today or tomorrow, and you will get today's notes as well. Okay. I hope that's been interesting. So what have we done today? Just very quickly. Wow, where's my file? So we had a look at, just very quickly, skews and kurtosis. I just wanted to remind you, these are the third and the fourth moment in the moment generating function. We had a look at, we picked up from where we left off on convexity adjustments last week, and I showed you a numerical example, and I will upload or re-upload the spreadsheet. Feel free to play around with it. And then we had a talk on the moment generating function itself, and then we had a look at the Gersdorff change of measure. For those of you who were a little bit late, I just want to let you know 3 things, I guess. So, last lecture, I'll write them in the notes. So please listen carefully. So last lecture, last tutorial, and I guess the last exam, or final exam if you want. Last lecture is today. You know that. In WMY, is it 407? Somewhere on the 4th floor. The last tube will be next week on Tuesday. If you can come, you are very welcome to. If for some reason you can't, then it's fine. This one is actually in YIA. What did I say the room was? 401. Well, actually, it's in the slides. A bit further down. Yeah, YA 401. I'm just really summarizing it for you. And the last exam is on June the 8th in the afternoon. Now, this will be downstairs, AIT. We are in AIT. G04 is a nice building, it's a nice room, nice and comfortable and spacious. Okay? Thank you for listening to me. And if you need to sign your attendance, you can do that after we finish. I'm just going to save this recording, and then you can sign your attendance. So how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 people. Please don't take pictures of this code and then send it around for people to sign the attendance, because I know who is here and who isn't. Okay? So please don't do that. All right, so let me just save this file. Thank you one time. See you in the afternoon. Bye.